Hi everyone, in this video I'd like to work on introducing the inverse trig functions. So basically we just have to start off with what is our goal, what should the inverse of sine, cosine, and tangent do, and then we'll work our way through some examples and try and get a handle on them. So we are going to focus on sine, cosine, and tangent here. I'm not going to worry about inverse, secant, cosecant, or cotangent, other than just maybe to mention one thing that is not true about them. Okay, so notation stuff first, and then we'll get into what these functions actually do. To represent the inverse of sine, cosine, and tangent, there are actually two different notations that we can use. One is reminiscent of the f with the -1 exponent attached to it. So this would represent an inverse sine of x. The other is to call it arc sine of x. So these two are exactly the same thing, exactly the same. There is no difference other than how we write it. So I am fine with you writing either one of those, and I would expect you to be comfortable with me using either one of those. Similarly, for cosine, the inverse of cosine can be written like that, or like that. And for tangent, we get the tangent with the -1 or the arctan. Arc, oh, got an extra letter in there. Okay, if that is not completely illegible, arctan. Okay, so this is the notation we'll use for these functions. Now we want to talk about what their job actually is. So sine, cosine, and tangent have very specific jobs on the unit circle. And their inverses should do the exact opposite. So the idea is that sine inputs an arc length and outputs your y value. So if we're thinking unit circle, sine always inputs arc length and outputs the y value of the point at the end of that arc length. If this is true, then arcsine should be doing the exact opposite. Arcsine would want you to tell it your y value, and it would tell you back an arc length. We'll get a little more detail on what exactly the inverse trig functions do in a minute, so that's the general idea, but there is a little bit of detail about being careful about what answer you give. Okay, and likewise for cosine, cosine inputs an arc length and outputs an x value, which means arc cosine will input an x value and output an arc length. And then for tangent, tangent is going to input arc length and output slope, which means arctan should input slope and output arc length. So notice that for all of the inverse trig functions, the output is arc length for every single one. It doesn't matter if it's sine, cosine, tangent. The same would be true for inverse secant, inverse cosecant, inverse cotangent. And this is where the arc naming comes from. The arc sine outputs arc length, arc cosine outputs arc length, and arc tangent outputs arc length. Okay, so this is the basic idea of what we're going to call these functions and what they do. I want to do a little bit more background stuff. I want to talk about some domain restrictions that we have to create before we can actually look at these things. And then we'll move on to other videos with specific examples. Okay, so we have functions that now input a y value, an x value, or a slope, and output your arc length. Exactly the opposite of what our standard trig functions do. All right, so hopefully you can see this. This is drawn in really lightly. This is the graph of sine, drawn in here lightly. And what I'm hoping you've remembered from 141 in the beginning of the quarter is that we have some problems trying to find the inverse of functions that are not one-to-one. So if I draw a horizontal line in here, it's going to cross this graph infinitely many times. So I have lots and lots of problems. And if I try to do my usual flip over y equals x and see what the inverse looks like, I'm going to get, let's see, I have this. So this part will stay kind of the same, and what will happen is it'll be going back and forth as I go up. And from that, you can see hopefully even more that what I would draw to try and represent the inverse is not actually a function, which means we have a problem trying to find the inverse of this thing. So what you need to do is restrict the domain of this thing until it's 1-to-1, until it does pass the horizontal line test. So you can pick any chunk of this graph, the goal being to try to make sure that you get all possible outputs. So we want to get everything from -1 to 1 without repeating any. And there are many correct choices. So we could go from here to here. That would get the entire range without repeating any y values. From here to here, from here to here. So from any top to bottom or bottom to top would work. The one we're going to choose, because somebody has already chosen for us, and we will follow tradition, is this one. And let me label some scale here. So this is supposed to be a pi over 2 and pi, 3 pi over 2. And same thing on the other side. Okay, so we're going to restrict the domain of sine. So the blue one is sine x is restricted to, here, and we'll even use function notation, f of x equals. So restricting the domain to be -pi over 2 less than or equal to x less than or equal to pi over 2. So this is not the entire sine function. We're taking one small piece of the sine function, and we are using it to try and figure out what inverse for just that specific piece of the sine function or the unit circle. So if we want to figure out what the inverse looks like, we need to take this whole thing and we need to flip across y equals x. Let's see if we can kind of rough sketch that. So pi over 2 is about 1.57, which means there's a y value of 1.57, and then pi is about 3.14, so there's an x value of 3.14, and here's a y value of 3.14. Let's see if I can kind of follow it on this side as well. -3. Okay, so this is my little visual aid for what y equals x is looking like with my scale. So if I flip across y equals x, what happens is this point flip straight across to here, this one flips straight down to here, and our bend flip-flop. So it's now going something like this. And you can follow that point by point. This is pi over 2, 1. So it will flip to 1 pi over 2. Oh, except I'm not being careful here. I forgot my own scale. So 1, this is 1.57. So 1's actually a little closer to over here. And then -1 is out here just a little ways. So it's close, but looking a little crooked with my scale. So this is what an inverse sine looks like. It's this little tiny piece. The really big important thing here is to realize that, okay, so we have sine and we've restricted it down. Its domain is -pi over 2 to pi over 2. The range, we're still getting -1 to 1. When we look at f inverse of x, which is inverse sine of x, we should be getting the exact opposite. So now our x's should be between -1 and 1, and our y's should be between -pi over 2 and pi over 2. And in particular, this one is really important to realize. So yes, inverse sine inputs a y value and outputs an arc length, but to be really correct, we would have to say inverse sine inputs a y value and outputs the specific arc length between -pi over 2 and pi over 2 that goes with that y value. So really important to realize that inverse sine is only going to give you one of the infinitely many possible arc lengths, and it will always be the one between -pi over 2 and pi over 2. So personally, the visual I try and keep for myself is that it's always going to be on the right side of the unit circle. It's a little bit more than that because there are lots of arc lengths that land on the right side of the circle. So we're trying to find the arc length, the shortest arc length to get to the point. So if I get a y value up here, I'm going to get something in the ballpark of pi over 3. If I get an arc length that ends down here, I'm going to call it this negative pi over 6-ish, whatever that is. So you're always going to get an arc length between negative pi over 2 and pi over 2 from sine. Okay, similarly for cosine, and if you're feeling comfortable, I'll give you the restriction, and then you can try and draw the inverse and figure out your domain and range. So for this one, same idea, we want to go from a max to a min or a min to a max, and the piece that's traditionally chosen is this one. So this is 0 to pi. And like I said, if you're feeling pretty good about this, go ahead and pause now and see if you can reproduce what we did up above. So our function this time is a cosine x, and we're restricting the domain to be 0 to pi. And that is maintaining our typical range, -1 to 1. Okay, so this one, when we flip across y equals x, something like this, it's going to look a little bit more impressive than last time. So this point is 0, 1, and it flips across to 1, 0, which again, I don't have a great scale here. It's a little scrunched, so this might look kind of crooked, but that's about where 1, 0 would be. And then it should cross right here at the same point. And then this is pi over 2, 0, so we should hit 0 pi over 2, which is about a little bit over 1.5, 1.57. And then we get this end point that was at pi -1 being at -1 pi, 3.14-ish. Okay, let's see if I can get the bend right. So this flips across, so it's still bending this way. And this is still bending down. Okay, and again, it's not so much that I'm that worried about you remembering exactly what the picture looks like. I would hope that you kind of remember how to reproduce it, but the big thing here is the domain and range stuff. So my f inverse of x is a cosine inverse, or arc cosine of x. And it is going to input any x value between -1 and 1. And it's going to output arc lengths between 0 and pi. So if we're thinking about the unit circle for this one, our cosine, inverse cosine, will always assume that we're, I don't know why I drew the whole circle, we'll always assume that we're on the top half. So it's always going to be between 0 and pi. So top half isn't really quite enough, but that's the first thing that I think of is, okay, for our cosine, I have to be on the top. And then again, you want to pick the smallest one, so between 0 and pi. Notice that our goal, just like when we were restricting the domain of the sine wave, was to get the entire range of the function without hitting anything twice. So if we think about sine is outputting y values. If we want to get all the possible y values, we need to make sure we go all the way from the bottom to the top. If we don't want to repeat any y values, we need to either choose the left half or the right half. So someone's chosen the right half for us. Whereas with inverse cosine, if you want to hit all possible x values, you're going to have to go from the far left to the far right. And again, if you don't want to repeat any, you're either going to look exclusively at the top or exclusively at the bottom. And this time we chose the top. Okay, let's look at tangent really quick, and then we'll get into some examples of the kind of work we'll do to practice this. Okay, so for tangent, I think this is really hard to see, but I do have my asymptotes in here. So this is negative pi over 2 to pi over 2. And here's the middle chunk of tangent. Oh, and I'm doing this without even leading up to it. Okay, so it does this over and over and over again. And what I just drew is exactly what we want to restrict it down to. So we want one full branch of tangent. So we choose to go from one asymptote to the other. And once again, we just try and stick as close to the middle as possible. So this one of any of them is a graph I would try and remember. Again, I would hope you could reproduce it if you can remember that we're just using this middle chunk of tangent. You can always go back and flip over y equals x. So let's see, let me draw my y equals x in here again. Okay. So 0, 0 is going to stay put. The asymptotes, I have x equals pi over 2, which is going to become y equals pi over 2. So I have this asymptotic behavior that switches from vertical to horizontal. And then the x equals negative pi over 2 switches to y equals negative pi over 2. So again, excuse that this skews it a little. It makes it look fatter when I turn it on its side. Okay, so otherwise, this branch that was moving up higher and higher away from y equals x is going to flip down below and head this way. And this piece, actually I think the line should kind of follow it, where it's heading down below, further and further below y equals x, really steep there, is going to flip up above y equals x. And that's what arctangent looks like. And that's the whole thing. This isn't all of tangent. We've restricted the domain of tangent, but that's all there is to arctangent. So again, a good one to remember. I'm not going to have you guys practice a lot with graphing and doing transformations, but just this general shape is a really kind of neat and unique one. So it will come up later. Okay, so we have our function, which is arctan. And we've restricted it to be negative pi over 2 to pi over 2. This is a little different because there are asymptotes at negative pi over 2 and pi over 2, so these are strict inequality. And so this is domain. The range is all real numbers. Oh, shoot, I put the bold on the wrong one. So pretend there's no bold face here. This is just supposed to be R for range. And the inverse function, oh, what kind of nonsense do I have going on here? This was for tangent. My color coding worked, but my brain didn't. So tangent is from negative pi over 2 to pi over 2 with the domain of all reals. Inverse tangent has a domain of all reals. Did I just say it wrong again? Range of all reals, which means up here I have a domain of all reals. And then the range here is going to be negative pi over 2 to pi over 2. So on the unit circle, it actually matches up really nicely with sine. It's just that we have to leave out, I'm trying to make this big so you can really see it, the top and the bottom of the circle because tangent is undefined there. It's not because of anything about one-to-one. It's just because tangent is undefined when you have a vertical line. So for sine and tangent, it's that right half of the circle, and we're always trying to pick that nice little, the littlest possible arc length, so between negative pi over 2 and pi over 2. And for cosine, top half of the circle, 0 to pi. All right, so that's my intro on the inverse trig functions, and in the rest of our videos, we'll actually work through some examples and play around with them and just try to get used to them is the big thing. Thanks for watching.